Hey, everybody. So just a few more things to say about the derivative. And I'll put the definition of that up here again, but I kind of want to rewind and just look at the big picture once again. We started out with started out looking at something like this. We would have a function and some point on that function, f of a. So this function I've just decided is f. And we might look at a nearby point that we would call a plus h, f of a plus h. All right. And we would think about the secant line through this point a and this nearby point a plus h, right? H is some little amount, so a plus h is something near it. Again, I've drawn h positive, but it could be in either direction. And we had, so we're using this construction to compute the slope of the secant line, right? Secant line here, meaning just 2 points through the curve, the line connecting them, okay? Algebraically, this slope is just f of a plus h minus f of a over a plus h minus a, right? But of course, the a's cancel, and so how we usually write it is just over h, right? This is sometimes called a difference quotient. And we recognized that this, sorry, I just want to put a division up between these ideas, that this was, could be thought of as the average rate of change, right? That's what the average rate of change is. So we have like a graphical representation of what we were looking at, and then an algebraic representation, and then sort of maybe the intuitive or concept behind what these two things represent, right? So then we spent a whole bunch of time developing limits so that we could take these ideas and push them to their extreme. And so in the graphical representation, we take that value h, the difference between these 2 points, and shrink it to nothing. And instead of having a secant line, we end up with the slope of the tangent line. Right, as we shrink those points together. Algebraically, right, we give this slope of the tangent line a particular symbol, right, at the point A, is the limit as h goes to 0 of f of a plus h minus f of a all over h, right? We're shrinking that, and that's the algebraic way we do it with this new tool of the limit. And intuitively, we think of this as the instantaneous rate of change, right? Which is a little bit of a paradox, right? An instant is, there is no change, nothing's moving. And so how do we have a rate of change in an instant? That's where those limits came in, right? This bottom row, let's put this in a new color. This bottom row, these 3 concepts, instantaneous rate of change, slope of the tangent line, or this limit as h goes to 0 of f of a plus h minus f of a over h. These are 3 ways to think about the thing that we call the derivative, right? So when we talk about the derivative, we'll say more specifically the derivative of f of x at a, right? We want to always have these three concepts simultaneously there, right? We'll spend a lot of time taking limits, right? So we'll start to kind of focus on the algebraic notion, but we can't forget what this means geometrically when we look at the graph, the slope of the tangent line, or when we're applying it to something in the real world, it has a very clear meaning, this instantaneous rate of change. And we want to hold these ideas strongly in our head, right? One of the things that's going to happen shortly, in a couple more videos from now, we'll start developing a set of rules to make calculating these derivatives easier. You might notice that these limits are not always easy to take, right? We've done a few examples and we haven't really gotten into anything very complicated. They can very quickly become difficult to do. But we'll develop some rules, some shortcuts to make these kinds of things easier. We'll do some work so we don't have to keep repeating the same kind of work over and over again. And it's very easy when we develop these rules to start thinking about, oh, derivatives are just punching through these rules, right? But this is what the derivative is. Everything else is a shortcut. Everything else is something to make computations easier, but it doesn't change the meaning. This is how we want to think of the derivative. Let's do an example, keeping this stuff in mind. Let's suppose I have a function I'll call s of t, which is negative 4.9 t squared plus 19.6 t. Okay, let's say this is the position of an object. We'll say in meters. And maybe I'll put under position, it's the height of an object, in meters after t seconds, right? So this is a reasonable model if you were to launch an object straight up in the air at 19.6 meters per second. This is a good approximation to how high it will be after some amount of time. Right, friction and wind and things like that can change this, but this is a reasonable approximation. Okay. Suppose we want to, well, let's do a couple of things before we ask these questions. Let's sketch a graph of this. It's always good to practice sketching a graph. So we've got s of t is equal to negative 4.9 t squared plus 19.6 t. We might notice this is factorable, right? It might not be super obvious. I obviously set it up to be this way. So we have a nice factoring. The reason I want to factor it here is that it's very clear what the zeros are. T equals 0, this becomes 0. And at t equals 4, it becomes 0. And that helps me graph it. So let's put in a couple of axes. And so I know I have zeros here and out here, wherever I want 4 to be. And I know it's a downward facing parabola. So I'm not trying to make a perfect graph. More or less something like that. Looks a little bit wonky, but we'll call it good enough. Right now, obviously this parabola keeps going after those zeros in both directions mathematically, but if we're launching something from the ground, right, the 0 point represents where we begin. Our object travels up and then comes back down and at some point hits the ground and then this journey's over. So we're just going to draw the relevant piece of this puzzle. So the question I want to answer is, let's start with, what is the derivative at 1? All right, so on our graph, so halfway would be 2, there's 1. So we want to know the derivative at this point, right, approximately. And So that's at about 115, right? More or less, the point 115, but I'm not going to label it. When we're asked to compute the derivative, remember we're asking for the slope of this tangent line at that point. Okay, so that's what we're computing. There's our geometric representation, right? The slope of this line. So based on our graph, it's always good to have some notion in our head about what kind of answer we should get. My picture is sloppy enough that I wouldn't hope to try to guess how steep that is, right? Because I haven't done a very careful scale. I didn't check to see how high that vertex was. There's no indication, right? The true graph could be much, much taller, or it could be much shorter, right? So none of that is accurate enough to pick the try to make a guess at the value of that slope. But the picture is good enough to know that that point is on the left side of the vertex, and that slope certainly should be positive, right? So it's not a great approximation to just say it's going to be positive, but if we screw something up and get a negative number, I'll have a good idea that I should double check my work. So here's S prime of 1, the definition, the limit as h goes to 0 of S of 1 plus h minus S of 1 all over h. So we start putting things in, limit as h goes to 0. S of 1 plus h is going to look like negative 4 point. Actually, this is going to get a bit complicated. Let's do some scratch work off to the side, right? Because we're going to have to keep repeating this limit symbol. Things are going to get very crowded. So I'm going to do a little bit of work off to the side before finishing this. I'm going to compute S of 1 plus h. It's going to be negative 4.9, 1 plus h squared plus 19.6 times 1 plus h, which will be negative 4.9. We'll get 1, whoops, not plus yet. We'll get 1 plus 2h plus h squared plus 19.6 plus 19.6h. And then I can multiply this out and get 4.9 minus, so 4.9 times 2 is going to be negative 9.8h minus 4.9h squared. Plus 19.6 plus 19.6h. So there's our S of 1 plus h. Okay. I'm not going to simplify any further at this moment. I'm gonna, because I'm thinking ahead and noticing that I'm also going to subtract S of 1, which is going to have a lot of similar terms. So most of this is going to, or a lot of this is going to end up canceling. So I'm not going to do too much more work until I know what I have to do. S of 1 is simply negative 4.9 plus 19.6. which means S of 1 plus h minus S of 1, right? When we subtract, anything that is the same will disappear, right? So when we subtract S of 1, this negative 4.9 becomes positive and cancels this. This positive 19.6 is going to become negative and cancel this. So what will we be left with is negative 9.8h minus 4.9h squared plus 19.6h. These two things can be combined and we have 9.8h minus 4.9h squared. Okay. So now I'm going to take this back and put it in the numerator, right? This is my numerator now. So now I'm returning to this computation, the limit as h goes to 0. Actually, let's do one more thing. Notice they both have an h, so I'm going to go ahead and factor that h out. 9.8 minus 4.9h. Now we'll come back. We have h, 9.8 minus 4.9h over h. The h's cancel. We have a factor of h in the numerator and the denominator. And I'm left with 9.8 minus 4.9 h. We now have a polynomial in h, right? H is the variable here. It's a polynomial. It's a linear function, which is just a kind of polynomial. And we know we can just evaluate this by plugging in the value 0. And so the second term disappears. And we have that s prime of 1 is 9.8, okay? So the slope of this tangent line is 9.8, right? It's positive, like we said, at least, so I'm not guaranteed that I'm wrong by it being negative. What about what does it mean besides this geometric interpretation, right? So remember the third piece of the puzzle, we have the slope of the tangent line or this and this limit definition, and we've done both of those, right? We've done the limit definition and we understand that it's the slope of that tangent line. I could, for instance, write the equation of this line. So this point here is at 1, let's just call it s of 1. So the equation of the tangent line would be y minus s of 1 times the slope of 9.8 x minus 1. Right? You could compute s of 1 if you want to. But 13.7, in any event, right? So we've understood this part. What about that last piece, the instantaneous rate of change? Well, let's go back to our difference quotient here. Take this little piece out. Let's think about what this thing is. In the numerator, we have values of the function being subtracted from each other. The function is in meters, right? So we have whatever the number of meters s of 1 plus h is minus s of 1 meters, right? In the denominator, we have seconds, right? H is a thing we're putting into our variable t. It's seconds. And so this quotient has units of meters per second, right? In other words, it tells us it's the rate of change of meters with respect to seconds. How much do the meters change every time the seconds change? When we got an answer of 9.8, it's telling us that, for instance, this line, the slope being 9.8 means that if I change the input, which are representing seconds, by 1, the output increases by 9.8, right? That's what the line does. The function doesn't do exactly that. What it means is at that point, that's what it's doing. But of course, if we move off that point, the next point, gravity's pulling down on this object. It has now slowed down, and so that rate of change is changed. It's getting less, right? We know it's getting less looking at our picture, that by the time we get near the top, right, you can imagine throwing an object up, it slows down, it stops, and then it comes back down, speeding up as it goes, okay? So we have meters per second. That's our instantaneous rate of change. How, at that moment, how are the meters changing as the seconds change? We have a word for this. This is our velocity, right? So if we have a function s of t that gives us position, then s prime of t, maybe we'll write it as v of t. Sorry, let me say this a little differently. If s of t is our position, then s prime of 1, we might say, is v of 1, the velocity at t equals 1, right? Or we could compute it at another point and get a velocity at a different point, okay? So this is a really good example of this instantaneous rate of change that has a really solid meaning for us here, right? When we're just doing things with no real world context, mathematically, it's not as easy to think about. The geometric still applies. We have the graphs, and the algebraic still applies. But if we give these some meanings, this instantaneous rate of change makes sense, right? We can track where an object is at each moment. How fast it's going is telling us how where it is changes as time changes, right? If we did a different kind of function, right? If we had f of x is the profit in dollars given x units are produced, right? So some function from a business model, right? Then if we looked at, for instance, f prime at, I don't know, 100 units produced, well, we would have dollars over units, right? It's how does our profit change if we change the number of units we produce, right? And that's not always going to be the same, right? You can imagine if you were going to produce some kind of widget and you needed to build a factory in the very beginning, you probably don't get any profit when you make them, because until you've covered the costs of that building that factory, you're losing money. But at some point you cross that barrier and you're making profit, and after that you're making more and more profit. So this might tell you this rate of change, profit with respect to units. If I change the number of units I produce by 1, how much will my profit change? Or we could have pressure, like air pressure at altitude A, right? Then if we computed P prime of 3, let's say, our units would be maybe atmospheres over kilometers, right? Changing a kilometer will change my atmosphere by how much? That's what this instantaneous rate of change would tell us. Okay, I just wanted to make sure we had that connection very strong. These 3 ways to think about the derivative at a point. Slope of the tangent line at that point, the result of this limit, that's kind of our official mathematical definition, but we always want to connect it to the other 2 things, the slope of the tangent line and this instantaneous rate of change when we've got some kind of context. Okay, that's going to do it. Thanks, everybody. I will see you next time.